So the last type of calculation that we'll look at for titration is what we call a back titration calculation. But really, all the previous questions that we have been doing are variations of a back titration calculation. It's where you have a titration calculation and then you have a calculation after that, okay? The reason why it's called a back titration, if we ever think back to like the dilution questions that we've done, we had an original amount that we need to get to, or we're trying to find, but we've diluted it and then we did a titration with it. So then you work backwards from that titration, right? That's why it's called back titration. And this is a similar question, just not with dilution this time, okay? So if we have a look at example 10, it says that we've got an ingestion tablet that was crushed up, 25 mils of 1 mole per liter hydrochloric acid was added in excess, and then the resulting solution was calculated against sodium hydroxide, calculate the mass of the calcium carbonate. So that's the main ingredient in the tablet. So what's essentially happened is we've got sort of a tablet here. You sort of crush it up, right? And then the tablet gets reacted with HCl, and then you've got your tablet here, okay? And then what happens is there's excess HCl, right? So the tablet's completely neutralized, and then you take this sort of excess HCl, and then you do a titration with it, right? So we've got our titration set up like so similar to what we were doing before. Yeah, so we've got our titration set up, and what you've essentially done is you've taken that excess HCl and titrated it against NaOH, okay? It was 0.5 mole per liter concentration of NaOH, and you required 25.8 mils of it, okay? So the back titration, with all back titration questions, you start off with the actual titration calculation itself and then work backwards, right? Because if we find the amount of excess HCl, we can then find out how much HCl was used, and then we can work backwards and find out the mass of the carbonate ion. Okay, so the equation for the titration is HCl plus NaOH going to form H2O plus NaCl, okay? And so writing down underneath what we know, we used 25.8 milliliters of sodium hydroxide, 0.5 mole per liter of that, okay? And then with the HCl, let's think about whether we know the concentration or the volume and what we're trying to find. In the previous questions, a lot of time we find the concentration, but in this case, it didn't tell us how much volume of HCl that we used. And it's a bit hard for us to find because we just used whatever was in excess. So that's a bit hard to measure. But we do know the concentration because the original concentration was 1 mole per liter. So the concentration there is 1 mole per liter. Same again, no 3, calculate the fourth, right? So now what we're doing, instead of calculating concentration, we're calculating the volume of HCl that we used, okay? So now to calculate that, we've first got to find the number of moles of sodium hydroxide that we've used. So that's concentration times volume, like we usually do. And that'll give us 0.0129 moles, okay? And that's equal to the number of moles of HCl present, right? Because it's a 1-to-1 ratio, so that's 0.0129 moles. And so therefore, if we want our volume of HCl now, remember concentration, C equals N on V, right? So therefore, if we want to find volume, that's number of moles divided by concentration. So if we take the number of moles, 129 divided by the concentration, which was conveniently 1, we're going to get 0.0129. Remember, volume's always in liters, and that's liters. And so if we convert that to milliliters, that's 12.9 milliliters of HCl. What does that mean and why is that important? It means that in the titration, we actually had 12.9 milliliters of HCl, right? But then what did we say we originally used, or we originally started with? We originally started with 25 mils of HCl. So what that actually means is the excess amount of HCl was actually 12.9 milliliters. And in this reaction here, we used 25 minus 12.9 milliliters of HCl, because this is the excess HCl. So the amount of HCl we actually use in this reaction would be the amount we started with minus the amount that was in excess. Okay, so that brings us on to the second calculation, because what was the calculation that was going on here with the crushed up tablet and the HCl? Well, it's the crushed up tablet calcium carbonate reacting with the HCl to form calcium chloride plus H2O, because it's carbonate, you're going to have CO2 as well. And so that's just putting a 2 in front of there. So to write down what we know underneath, well, we don't know anything about the calcium carbonate. That's what we need to find. The concentration of the hydrochloric acid is 1 mole per liter. That doesn't change, right? Because we originally have 1 mole per liter. But what's interesting is in this actual reaction here, so if we just call this sort of reaction 1, right? What's interesting is that we didn't actually use all 25 mils, because part of that 25 mils was transferred over to, we'll call this reaction 2, which is this reaction here, and then we used actually that amount to do a titration. So we found in reaction 2 that we used 12.9 mils of HCl. So in reaction 1, the volume of HCl that was actually used wasn't all 25. It would have been 25 mils minus the 12.9 mils that was left over and then subsequently used in reaction 2. So what do we have left over? Well, it's 12.1 milliliters, okay? So that's the volume of HCl that we've essentially used up in that first reaction there, okay? So so the concentration is 1 mole per liter, we know that, and then the volume we know is now 12.1 milliliters, okay? We have concentration, we have volume. What can we find? We can now find the number of moles of HCl, which is the concentration times the volume, so 0.0121. Okay, and then that's going to just be very easy, 0.0121, and that's going to then be, using our mole ratios 2 to 1, the number of moles of calcium carbonate is going to be half of that, so half times the number of moles of HCl. Okay, that's going to be 6.05 times 10 to the negative 3. So we now have the number of moles of calcium carbonate, and then ultimately the question wants us to find the mass. So the calcium carbonate, mass of calcium carbonate, that's just going to be the number of moles times it by the molar mass. So by 40.08 plus 12.01 plus 3 times 16 plus 3 times. Okay, so plugging all that into our calculator, we get 0.606. We'll just do 3 grams, okay? So essentially we have 0.606 grams of calcium carbonate in our tablet, all right? So just to recap the main points of this question, right? We had a tablet, we crushed it up, we reacted with HCl, okay? 25 mils of it, 1 mole per liter, but there was excess HCl. So it means the tablet ran out, right? The calcium carbonate in the tablet ran out. And then we took that excess HCl and we titrated it against sodium hydroxide. So we titrated against sodium hydroxide. We knew the volume and the concentration of sodium hydroxide, which meant we could find the number of moles of sodium hydroxide. Then we can use that information to find the volume of HCl, because we knew the concentration of HCl was 1 mole per liter. So we found a volume of HCl, and that's how much HCl was used in the titration, which corresponds with the amount of HCl that would have been excess in this first reaction here. Okay, so if we write out the equation for the first reaction, we know we started with a concentration of 1 mole per liter of HCl, and we know then we would have used up 12.1 mils of that HCl, because we have 12.9 mils of the HCl in excess. And we ultimately started with 25. So we found out how much volume was actually used in this reaction. And then we have concentration and volume, which allows us to find the number of moles of HCl. And so then the number of moles of HCl would have completely reacted with the calcium carbonate. So we then find the number of moles of the calcium carbonate. Once we found the number of moles of the calcium carbonate using mole ratios, then we can find the mass of calcium carbonate. And that's pretty much it.